So in this video we're going to see that electrons are in fact waves. Now it was first realised in 1924 by Louis de Broglie that if photons, which were originally thought of as light, were in fact particles as well, then wouldn't it make sense for electrons, which we think of as particles, to also be waves? And for photons we had our equation to describe their momentum, P is equal to h over lambda. Well, de Broglie just rearranged this equation and said, well, lambda equals h over p. That applies to an electron, and that will allow us to calculate the wavelength of the electron. Now, in 1927, Davidson and Germer did an experiment. They hadn't heard about de Broglie's hypothesis about electrons being waves. They did an experiment where they had a crystal and they shone electrons onto the crystal, and because a crystal's got layers in its structure, they actually observed an interference pattern as they looked at the reflected electrons from different angles. And interference is a wave phenomenon, so this was the first experimental evidence that electrons were indeed waves. Since then, there's been many experiments which have been done to show the wave nature of electrons. So Young's double slit experiments, single slit experiments, all these things which show the interference of electrons and so their wave nature. And in fact, there's lots of technologies nowadays which make use of the wave nature of electrons. So electron microscopes, for example, can look at very fine structure because the wavelength of an electron is much smaller than the wavelength of light. They've also managed to make protons and neutrons act as waves, so these have even smaller wavelengths than electrons. So let's do an example now where we'll calculate the wavelength of an electron. So the problem: what is the de Broglie wavelength of an electron with a kinetic energy of 120 electron volts? So we're going to need to use our de Broglie wavelength equation. Lambda is equal to h over p, and p, that's the momentum, is equal to mv. And what we're told about is the kinetic energy, which is a half mv squared. So we know this, and to work out the wavelength, we need to get P. So we need to convert our kinetic energy to being in the form in terms of P. So we can write this as a half m squared v squared on m. We've just we've times it by m and m there. And why we've done that is so that now we can say this is a half p squared on m, which allows us to rearrange. We're trying to find the momentum. So we've got p squared is equal to mk times 2. So that tells us that p is equal to the square root of 2mk. So now what we can do is calculate p, and then we'll be able to get this wavelength. Okay, so p is equal to the square root of 2 times m. Now m, that's the mass of an electron, so 9.109 times 10 to the minus 31. And then we need to times it by the kinetic energy, which is 120 electron volts. But to get it from electron volts to joules, which is what we need, SI units, we multiply that by 1.602 times 10 to the minus 19, the charge on an electron. Okay, solving this on the calculator, we get 5.918 times 10 to the minus 24. So now we can calculate lambda is equal to h, which is 6.626 times 10 to the minus 34, over p, which we've just calculated, 5.918 times 10 to the minus 24. And solving this on the calculator, we get 1.12 times 10 to the minus 10 meters, which we could write as 1.12 angstroms, or a more normal way to write this would be 112 picometers. Pico's 10 to the minus 12. So we've now calculated the wavelength of the electron. This is around about the size of an atom.